You've spent about a third of your life working on this mission. What are you feeling now?
It's a pretty amazing emotional state. When you get to a point like this in your career, an event that you've worked for, in my case, over 16 years to get here, you kind of think back to all the people who have helped you.
OSIRIS-REx is 3 missions in one to make that kind of exploration cost-effectively for not much more than the price of a blockbuster movie.
As OSIRIS-REx was actually out in space and began making its approach closer and closer to the asteroid, it used its suite of onboard camera instruments to actually image the surface in increasing detail. Bennu grew in detail from just a few tiny pixels on our screen to this super high-resolution world littered with giant, rugged boulders.
Bennu is a totally different creature. It really looks like a pile of rubble.
There were obviously a lot of firsts in this mission, and there was a time when you said, a lot of what ifs, basically. What if we could actually send a spacecraft to an asteroid? What if we really could bring back a sample of the solar system from billions of years ago?
But it's always really rewarding, like even when you saw the first, approach picture to Bennu, it's like, oh my gosh, that's our target.
The tag is just the pinnacle of the mission so far. Getting the sample back to Earth is obviously going to be the great event of the entire mission.
I think one of the age-old human questions, perhaps going back to the beginning of humanity, is, are we alone in the universe? And that maps directly into, why are we here?
We want to understand the origin of the Earth, the origin of the Moon, the other terrestrial planets, but the earliest histories of those bodies is wiped out. We had the late heavy bombardment 500 million years after solar system evolution, and that's what dominates the surface of the Moon. The Earth is a very active geologic body. You've got volcanoes, you've got earthquakes, you've got the hydrologic cycle. It's reworked the surface many, many times, and we worked very hard even to go back 3 billion years to understand what happened in that period of our planet's history. The asteroids record the earliest stages of the solar system, from even events that took place before our solar system formed, the stages of protostellar collapse and the formation of the protoplanetary disk, and then the formation of hydrated minerals and organic molecules in the first 10 million years of solar system history. Asteroid Bennu is a time capsule from the earliest stages of solar system evolution.
Our main goal is to collect a sample of an asteroid and return it to Earth. But why was Bennu chosen as the target destination asteroid for OSIRIS-REx? Well, the science team took into account 3 criteria when making that selection. We need an asteroid that we can easily travel to, retrieve a sample from, and return to Earth all within a few years' time.
And then we needed to think about the fact that we're a solar-powered spacecraft. We couldn't get too far out into the solar system. We couldn't get too close to the sun. So that constrained the size of the orbit. So with all of those constraints, we got down to a few dozen asteroids. And then we looked at spacecraft safety. We needed something that was kind of large and not spinning very rapidly so that we could do our proximity operations and get the spacecraft down to the surface and get that sample.
When an asteroid is smaller than those 200 meters in terms of diameter, it actually spins rather quickly. And it can rotate rapidly enough to where even some material could potentially be ejected off the surface. We want this to be a safe, smooth, slow high five of that surface. Our third criteria was composition. Thanks to telescopic observations in the visible and the infrared, as well as in radar, Bennu currently is the best understood asteroid not yet visited by a spacecraft.
So we want to go to a carbonaceous asteroid that's recorded over 4.5 billion years of solar system history. And then finally, after all of that, we had about 5 asteroids left. We wanted to go to the one with the highest scientific value. So after all of those constraints were on the table and we looked at the millions of asteroids that are in the solar system, Bennu rose to the top as the optimum target for OSIRIS-REx.
What makes Bennu so special? Why is it named Bennu? Who got to name it?
Oh, hey, Carl, how's it going?
Hey! Okay, how you doing?
And after we selected it as a target of our mission, we worked to run an international naming contest. We received over 8,000 entries. Many of them were awesome asteroid names. I couldn't believe there weren't asteroids already named some of the submissions that we got. We chose Bennu because it ties into the Osiris. It's an Egyptian heron that's related to our theme on the mission. And the winner was Michael Puzio from North Carolina, and he said that the spacecraft looked like a heron in flight when it went to go down and capture the sample. So we thought that was a really excellent connection between our engineering, our science, and our themes, and that was why it was the winner of the contest.
What I personally am most excited about for the OSIRIS-REx mission will be the first images that we get when approaching Bennu. So right now we have a sense of what Bennu looks like and what its shape is from ground-based assets like Arecibo and the Goldstone radars. But we won't know what the shape is completely, we won't have a perfect sense of it until we actually encounter Bennu and get images that reveal what it looks like as a world.
This is a spacecraft that is primitive, that dates back to over 4.5 billion years ago, and it's carbon rich, so we know there's potential for organic molecules to be there within that material we bring back. So it's important because it helps us understand really the formation of our solar system. That's kind of a big deal. Yeah.
It is fantastic to be able to return a sample to the Earth. When you design a mission and say have a chemistry lab that you want to build to send to an object to study, you're limited by the space and the power and the data rate and all kinds of other things. You, for example, cannot have a mile-wide synchrotron put on a spacecraft. You need to design your instruments early so that they can be well understood and incorporated. You can't make changes as new discoveries happen, as new technologies are developed. When you return a sample to the Earth, you can take advantage of every new technology developed, of new minds all around the world thinking about new ways to analyze the sample.
We have learned a lot of information from previous missions to asteroids and comets, and we learned from that primarily to spend the time to characterize the asteroid and then practice and simulate your sampling maneuver many times over. We have a unique design where we put this TAGSAM device onto the surface of the asteroid, and then we blow down high-pressure nitrogen gas, kind of agitate the soil, and then basically scoop it up in a giant air filter. That whole process takes 5 seconds, so it's kind of get in, get the sample, and get out of there.
This actually started as a contest where we wanted to know what is the best way to actually bring back a sample, and it turns out that somebody used a solo cup and an air compressor in their driveway, and that's what actually started the TAGSAM technology. It's a reverse vacuum.
Our design is to bounce off the surface of the asteroid. In fact, we've got a spring in the forearm of our TAGSAM device, which is acting literally like a pogo stick to push us off the surface of the asteroid after we make that initial contact. So from everything that I've seen, trying to bounce off the surface of the asteroid is the easiest way to get that material.
How many of the larger rocks
Did you get many large ones?
Mostly the smaller aggregate dust particles reflected.
So what's behind me here is the asteroid wall. It is 50 feet tall and was used for testing of OSIRIS-REx. It is representative of what we think the surface of Bennu looks like. It is also painted to be 3% reflective, which is what we believe the reflectivity is on Bennu.
So being involved in the OSIRIS mission is really awesome. It is giving me the opportunity to do something that I would like to do as a career, which is do spacecraft instrumentation. The student team is going to be, several engineering students and software students building some component of a spacecraft.
Of all the missions I've worked on, OSIRIS-REx has a really unique relationship with our science teams in development. Traditionally, as the engineering side of the spacecraft, we build the spacecraft in order to sort of serve the science teams in this mission. But in this case, for us, the engineering and the science is much more intertwined than normal. The scientists are needed for all of the information from their science instruments on the spacecraft, as well as all their analysis pre-launch, is what enables us to direct the spacecraft, guide it, and land safely on the surface. And so without the science input, we can't accomplish our engineering goals either.
We started formal assembly and test operations in March of 2015. We did that in a clean room because it's so important for us to maintain the pristine nature of the samples. So we had extra controls that were required for us on this mission that we haven't had in the past. We then tested the spacecraft through a series of environments that mimic what it sees from the time that the rocket launches all the way until the sample lands safely in the desert in 2023. We tested it over temperature, we tested it over pressure, vacuum, no vacuum. We tested it in vibration environments, and we tested it through the acoustic environment that it sees during the launch environment. It really took a whole team of people in order to make sure that the efforts were successful.
The most exciting thing is the people. We have one of the most fantastic teams around. Everybody from the folks who actually built our spacecraft to doing all of the ATLO, the testing that we've been doing in preparation from launch, the launch vehicle crew, and everybody down here at Kennedy Space Center who's been prepping us for launch, to our communications team. Everyone around us is fantastic. This is one of the best science teams out there. I'm super honored and privileged to be a part. If you want to talk about terms of the actual mission itself, getting that sample back to Earth is the most exciting part, because we will have something that preserves material from over 4.5 billion years ago. Who doesn't want that?
Methodical, careful process.
It kind of describes space business in general.
Now we have a built vehicle.
We have a vehicle, and it's ready to go.
And now they finished the processing on it. We'll be ready to launch today.
Excellent. Spacecraft safely delivered out to the vertical integration facility, and then it was hoisted atop the Atlas Centaur rocket.
It was. It was a good day to do that. Yeah. So we found a window where the winds were down, where the clouds allowed us to do it. We got up there. The ULA guys have all been spectacular as well. Like I said, we've had a really good time here, and we're looking forward to a spectacular launch as well.
1 minute, 21 seconds and counting.
Coordinator, clear to proceed. Launch director, LD is go and you have permission to launch. Proceeding with the count.
What makes you excited about watching a rocket launch?
What doesn't make you excited about watching a rocket launch? I hear that you're gonna feel the shock waves and the sound waves.
T-minus 1 minute and counting.
Status. Range green.
No issues with the range. Everything continues to be go. The final status check of Atlas, Centaur, and OSIRIS-REx readiness will be conducted 25 seconds away from launch. T-minus 40 seconds.
Stable at step 3.
$28. 25.
Status check.
Go Atlas.
Go Centaur. Go OSIRIS-REx.
Everyone is go. Standing by for launch. Ten seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx. Its 7-year mission to boldly go to the asteroid Bennu and back.
It's looking good. Starting pump speeds and injector pressures are within family. Main chamber pressures have plateaued, begun to ramp off.
Heard the voice of Marty Malinowski. The Atlas has begun a pitch and yaw pretty sure to its 1.5 degrees inclination from the equator.
As our main chamber pressure is almost plateaued at this point. Marty 180, injector pressures are good.
45 seconds of flight.
Program is complete. Boosters throttled down.
And the Atlas rocket carrying OSIRIS-REx has gone supersonic. Standing by to pass through max Q, maximum aerodynamic pressure.
Max Q, vehicle migrates continue to look good.
This is the point when the mechanical stress on the rocket reaches its peak because of the rocket's velocity and resistance created by the Earth's atmosphere.
Signatures look good. Current altitude is 14 miles. Downrange distance is 9 miles. Current velocity 2,488 miles per hour. Range track shows vehicle progressing down the middle of the range.
And you see the solid rocket booster jettison.
Separation looks good.
worked hard to get to this point. The best times are ahead of us. We are going to get to asteroid Bennu. We're going to map it. We're going to pick that site. We're going to get that sample, and we're going to bring it back to Earth in 2023. And so I can't tell you how thrilled I was this evening. It was a wild, emotional ride, thinking of everybody that's with us, that's not with us, and all of the anomalies that we troubleshot, none of those came up. We hit all of our milestones within seconds of the predicts. Really kicked that field goal right down the center of the goalpost. So NASA has done it again, absolutely.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had this sandy surface that we were expecting and what we had designed to.
The challenge of finding a tag site on Bennu that met our original criteria was very hard.
But quite honestly, this team thrives on challenge. So even though we knew we had work to go, I never doubted for a moment we would solve that puzzle, that we would crack that nut and we would safely get the spacecraft down to the surface. We had kind of expected the unexpected. This team was ready to be surprised.